All right, I think we're about ready to get started here. Good morning, everyone. We are going to start our last standard, standard 23 on volumes of solids of revolution. If I look at our Google Calendar here, the Google Doc, kind of what we've got left for the rest of the school year. This week and next week focuses on standard of 23, on finding the volumes of solids of revolution using definite integrals, such method as the disk method, washer method, shell method. We'll get into those over the next couple weeks. I've got quiz 10 planned for a week from Thursday, the last kind of traditional assessment, and then the course final a week later. You'll find study guides linked below, as well as on our course Schoology page. If you haven't already, for Standard 23, gone and taken a look at some of the tutorial videos that I've got posted on Schoology. This is kind of a visual, graphical content, and I'm already kind of limited by my own artistic abilities, made even worse by trying to draw on a laptop as a result of this distance learning we've got to work through. I would highly suggest going back to take a look at those videos because they do a much better job of drawing and describing the visual aspect of what we're talking about here in volumes of solids of revolution. I'll do my best. But for now, let's take a look at some slides I had prepared. What we're going to do is create a solid by revolving a region about an axis. Sometimes it's the x-axis, y-axis, or another arbitrary line. So as I can see here, we're going to rotate the region below the graph of y equals e to the x about the x-axis to create kind of this funnel-looking object, cone funnel-looking object. Our task is to use a definite integral to find the volume of this solid as it's being revolved around the axis of revolution, the x-axis. What we're talking about today is the disk method. There's about 2 or 3 different methods of computing the volumes of solids of revolution. Sometimes, in some cases, some of these methods work better than others. We'll talk about that later. So as you can see on the interior of this diagram, there's almost a coin or a disc-looking object. And what that is, from a geometric standpoint, is actually a little cylinder, kind of a flat coin cylinder-looking object. And the volume of a cylinder is pi times the radius squared times the height. What our goal here is, through the process of integration, is to sum up all the volumes of all of the different disks that would be contained within this region. Now over here to the right, I did my own kind of best freehand drawing of what's in that diagram. Looking at just the top half above the x-axis. This curve again is y equals e to the x, and we're rotating it around the x-axis. We need to find some formulas for this volume expression down below. Pi times the radius squared times dx for the height. The radius of this region is basically the height above the x-axis. In other words, that's going to be e to the x. In terms of x, the radius would be e to the x. The height of this disk, or depth, is going to be dx. the change in x along the x-axis, giving us the depth of that disk. Whatever bounds you might have from A to B, be it from 0 to 5, 1 to 8, whatever, the volume of this solid of revolution is given as pi times the definite integral from A to B of e to the x squared dx. A better idea of what is done is on this GeoGebra link here. I had it loaded. It was ready to go a second ago, and now it's not loading for some reason. Let's see if we can move on and come back to it later. We'll just look at a couple sample questions here while that hopefully gets loaded. All right, so problem 1. Find the volume of the solid generated by revolving the region bounded by the graphs of f of x equals the square root of sine x for x values between 0 and pi about the x-axis. All right, so here is a picture on Desmos of that region. We're going to take this region and rotate it about the x-axis between 0 and pi. One of the best things that I can do to recommend as you're trying to solve some of these questions is to draw a picture. Here's 0, and pi. And our function which is the square root sine x. We're going to rotate that around the x-axis. Since this is the disk method, I typically will draw some sort of rectangle representing one of these disks. So for the disk method, we're looking at the definite integral from a to b of r of x squared dx. Don't forget the pi. It's like we're taking the sum of an infinite number of each of these disks and adding them all together to represent the overall volume of this solid of revolution. All right, here's a better picture of that GeoGebra link. I think it just loaded. As we can see below, we've got some of these disks. I can let the number of disks increase, giving me a more and more smooth solid. Through our definite integral, we're going to find the volume of each of these disks and add them all together. I rotate my figure around the x-axis. As you can see over on the right, kind of creates that almost cup-shaped thing. The height and radius are shown over here to the left. Each of these rectangles has a radius that is equal to the function in terms of x. In this case, it's 2 square root of x. The height or depth is some distance x, call it dx. And that's kind of our goal here for each of these questions, is to find a formula in terms of our definite integral to get the volumes of these solids of revolution. So in this case here, each of these disks has a radius that's going to be in terms of x as the square root of sine x. So let's use that to set up our definite integral. Pi times the definite integral from 0 to pi of the square root of sine x squared dx. Let me pause here for a minute. If you guys have any questions, go ahead and speak up now, please. Take yourself off mute and let me know. All right, let's keep going. I'm going to simplify this as pi times the definite integral from 0 to pi of, well, if I square the square root of sine x, that just leaves me sine x dx. What is the antiderivative of sine? I believe that's going to be what? Negative cosine? So pi times negative cosine pi minus negative cosine of 0. Cosine of pi should be negative 1. The negative of that would be positive 1. Cosine of 0 is positive 1, but then net minus negative 1. I think I'm going to get 2 pi. 1 minus negative 1 is 2 times pi makes 2 pi. Of course, we can always check that on Desmos. The integral from 0 to pi of quantity f of x squared dx is going to be 2. Obviously, I have the pi out in front to make that 2 pi. If I rotate this region around the x-axis, the volume of that solid is equal to 2 pi. Any questions so far? Okay. If not, let's keep going. Another question on finding the volume of solid of revolution. It's a little bit different setup. It says find the volume of the solid formed by revolving the region bounded by y equals the square root of 16 minus x squared, x equals 0, and y equals 0 about the y-axis. So rather than a horizontal x-axis of revolution, now we're revolving around the y-axis, a vertical axis of revolution. And that's going to change how I'm going to set up this question and how I'm going to generate this volume. So let's go ahead and take a look at what this would be on Desmos. Okay, so if I look at kind of this top right corner, it's almost like this top quarter circle is my region bounded by these three functions: x equals 0, y equals 0, and y equals the square root of 16 minus x squared. So as with everything, let's draw a quick picture. All right, so there's 4 on the x-axis, 4 on the y-axis, and this is y equals square root of 16 minus x squared. Okay, so there's the region bounded by our three given functions. We are rotating about the y-axis. This question is different than the previous one because we were rotating around the x-axis here. So our disk was running perpendicular to that, and as it's rotated, it creates our solid. Here on this question, now we're rotating around the y-axis. So our disk is going to be sitting on top of that, running perpendicular, running horizontal. The depth or height of that disk is now no longer a dx, a distance along the x-axis. It's a dy. It's a distance on the y-axis. Meaning that this definite integral is not going to be in terms of x, but in terms of y. The volume is pi times some definite integral from a to b of r of y, quantity squared, dy. The radius needs to be in terms of y. It's some equation that's going to take our x value for any x value. How far out on the y-axis are we having our radius? So if I look at my equation here, presents an interesting challenge. That equation, that function is y in terms of x. My definite integral needs to be in terms of y. So I need to solve that function and get it in terms of y, get it in terms of x in terms of y. So let's take that function and solve for the other variable. So if I square each side, I'll get y squared equal to 16 minus x squared. I'm going to switch these two around. So let's call this x squared equals 16 minus y squared. Once I add x squared and subtract y squared from either side. And now we'll take the radical. X equals the square root of 16 minus y squared. And that's what our r of y is equal to. So pi times the definite integral from 0 to 4 of the square root of 16 minus y squared squared dy. I'm using 0 to 4 as the upper and lower bounds of the definite integral because it goes from 0 to 4 along the y-axis. I'm using the square root of 16 minus y squared because that would be the length out from the y-axis for any given y value between 0 and 4. Questions there? Okay. Let's proceed then. Pi times the definite integral from 0 to 4. If I square a square root, that leaves me 16 minus y squared dy. Substituting, let's see, finding the antiderivative. Pi times 16y minus y to the third over 3, or 1/3 y cubed, between 0 and 4. Let's see, I don't think I need to plug in 0, so let's just plug in 4. Pi times 16 times 4 is 64, minus 4 to the third over 3 would be 64 thirds. If I find a common denominator, that's 192 thirds. (192 minus 64 is 128 thirds times pi to make 128 pi over 3. Questions so far, guys? Please let me know if you have anything that I can help you with. Is anything not making sense? This one's a bit more difficult because we had to do a dy definite integral rather than dx. I had to do that because I was rotating around the y-axis, a vertical axis revolution, as opposed to the x-axis, a horizontal. Okay. If there's nothing, I did have one more I'd like to look at this morning. Okay. We've done an x-axis, y-axis. This is another example where I rotate around an arbitrary line, neither the x nor the y-axis. So reading this question here, find the volume of the solid formed by revolving the region bounded by y equals 1/2 x cubed, y equals 4, and x equals 0, about the line y equals 4. So I'm rotating around a line that's neither the x nor y-axis. So as with everything, let's pop on the Desmos and get a picture of what this might look like as a region. Okay, so be careful on which region we pick here. Sometimes people will be tempted to say that we're rotating this region, but actually we're rotating this region in the top corner because that is the region bounded by all three of these functions, these given equations. And once again, we're rotating around this green line on top, y equal 4. That went out to 2. Okay. Mm-hmm. So there's a decent picture of what our region looks like. We are rotating about the line y equals 4. And this curve is y equals 1/2 x cubed. Since this is the disk method, let's draw a rectangle to represent one of these disks that we're using to find the volume of the solid. That disk is sitting right on top of our axis of revolution. We need to come up with the radius for that disk, and it is going to be in terms of x, which is nice. Rather than the dy integral in the previous example, this is a horizontal axis of rotation, and the depth or height of that disk is some distance x dx rather than dy. Okay, so our challenge is to come up with some formula for the radius. Okay, so this region here, that's 1/2 x cubed. This region from top to bottom, that's 4. What I want is the difference of the two for this radius, that length for the disk. Like I said, it's just the difference of the two. 4 minus 1/2 x cubed. So the volume would be pi times the definite integral from 0 to 2, quantity 4 minus 1/2 x cubed, quantity squared, dx. Let me pause here for a minute. Questions at all, please? The radius is not 1/2 x cubed because that only gives me this part of the picture. I need 4 minus 1/2 x cubed to get the radius for the region we're rotating. Okay. So if
Mr. Hanson.
Yeah.
What really determines like what the r of x is equal to?
That is mostly determined by a couple different things. Number one would be what the region you're trying to rotate is, and what the axis of revolution that you're rotating around is going to be. If I was rotating around the x-axis, kind of a more typical, easier type question, my radius would be 1/2 x cubed. But I'm rotating by a region that's above that. I'm rotating around y equals 4. So the radius is going to be for this region on top. Well, this is 1/2 x cubed. The whole distance from top to bottom is just 4. What I want is the difference of the two right here. It's like the whole thing minus one piece to get me the other remaining piece. Does that make sense?
Yeah.
Okay. You really, I mean, it's just kind of takes some time for you to get kind of this put together visually. And always the best thing to do is to draw a picture on your own first. All right, so pi times the definite integral from 0 to 2 of, I'm going to write this out twice. Just so I can see how I'm going to expand it. Let's see, 4 times 4 is 16. 4 times a half x cubed is 2x cubed. A half x cubed times 4 is another 2x cubed, so minus 4x cubed. Half x cubed times half x cubed is actually it's a plus a fourth x to the sixth. Finding the antiderivative of that would be 16y minus x to the fourth, or 16x, or not y. The antiderivative of 1/4 x to the sixth would be x to the seventh, so a 28th x to the seventh. All right. Once again, I don't need to plug in 0. Let's just plug in 2. Pi times 16 times 2 is 32. 2 to the fourth is 16. Let's see, 2 to the seventh, is that 128? Yes, it is. Plus 128 over 28. Let's see, 32 minus 16 is 16. 128 28ths, what does that simplify down to? 32 sevenths. Finding a common denominator would be 16, that's 112 sevenths. Plus 32 sevenths. 112 plus 32 is 144 sevenths, or 144 pi over 7. Of course, we can always check that on Desmos. As a fraction, 144 pi over 7. Questions, please, guys. Okay, I got about 5 or 6 more minutes left. Let's see if we can't maybe try one on our own. Pull up the practice questions. See if these have any more difficulty loading the other document. you go ahead and try number 1. Set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the x-axis. As you can see, we're rotating the function y equal negative x plus 1 for x values between 0 and 1 about the x-axis. Why don't you go ahead and try that for a minute? We'll talk about it in just a second. Definite integral should be pi times the definite integral from 0 to 1 of quantity negative x plus 1 squared dx. dx gives us the height or depth of this little rectangular disk here. The radius is a function in terms of x given as negative x plus 1 for values between 0 and 1. We'll go ahead and evaluate if you'd like to work ahead or follow along. Let's call that 1 minus x times 1 minus x dx. One minus 2x plus x squared dx. So this would be pi times x minus x squared plus x to the third over 3 to evaluate between 0 and 1. Plugging in 1, not necessary to plug in 0, would give me 1 minus 1 plus 1/3. Well, this obviously just cancels. And so it should be pi times 1/3 or pi over 3. One-third pi or pi over 3. Checking on Desmos again. Gives me 1/3. So 1/3 times pi or pi over 3. Are there any questions there, guys? Okay. If you haven't already, it would be a great idea to go back and watch some of those videos that are on Schoology when it comes to the disk method. Otherwise, get into some of those practice questions, and we'll talk more about some of these definite integrals when it comes to the washer method in class on Wednesday. Otherwise, have a good rest of your morning. If you have any other questions, please don't hesitate to ask. I'd be more than willing to set up another video call for you if you'd like. Have a good day.
Bye.
Bye. Have a good one, guys.